Hi everyone. Today, two more examples predicting Bronsted-Lowry acid-base equilibrium. My first example has HSO4 a hydrogen sulfate ion, reacting with HCO3 a hydrogen carbonate ion. They're in equilibrium with some sulfate ions, SO4 and carbonic acid, H2CO3. My first step is to decide which chemical is the acid, which chemical is the base. This HSO4 became SO4 It lost an H+, it donated a proton, it's the acid. The HCO3 must then, by the process of elimination, be the base, but if we dig a little bit deeper, we see HCO3 became H2CO3, it gained an H+, it accepted a proton, it's the base. Now my next step is to go ahead and find the HSO4 in the acid column of the acid-base table in the data booklet. Here's the acid column, I'm looking for HSO4 there it is. Now I'm looking for HCO3 in the base column of that same table. Here's the base column. I'm just scanning, I'm searching. It might take a second, but I find the HCO3 in that column. Once I've located them, the acid is higher than the base. That means the products are favored. I have a slightly more intense second example. Here, the products are not given, so we have a little bit more work to put in order to decide which chemical is the acid, which one is the base. Our first move is, look at this, HPO4 a hydrogen phosphate ion. When I go to the table to locate it, I see that HPO4 is located down here, but I can also find it, not there. Find it right there. It shows up at the very bottom of the acid column and fairly low also in the base column. It's in both. It could be an acid or a base. This HOOCC001 is a hydrogen oxalate ion. When I go to the table, I can find it here in the acid column. I can find it here in the base column. As with the hydrogen phosphate ion, the hydrogen oxalate ion shows up in both columns of the table. It could be an acid or a base. Each of these two chemicals are what we call amphiprotic. If they could both be acids, we need to decide which one is going to behave like an acid in this particular acid-base equilibrium. The answer is going to be the stronger one. The hydrogen phosphate ion is way down here at the bottom. The hydrogen oxalate ion is higher up in the acid column. That means it's the stronger of the two acids, so it is going to be behaving like an acid. Then by a process of elimination, the hydrogen phosphate ion must be the base, or looking at the two chemicals in the base column, the one that's lower down is going to be the stronger base. It's the HPO4 it's the base in this particular equilibrium. Once I've identified the acid and the base, we can go ahead and execute the proton transfer. Let's move an H+ from the acid to the base. This turns out to be H2PO4 and we get the oxalate. We take an H+ from the acid and move it to the base to identify the products of this reaction. Finally, we need to predict the direction of the equilibrium. Are the products favored, or are the reactants favored? We were using the hydrogen oxalate ion as our acid, and here's the hydrogen phosphate ion as the base. The acid is higher up on the table than the base, which, just like our previous example, means that the products are favored. When we are asked to predict the direction of an acid-base equilibrium, we only have two options. Are the products favored, or are the reactants favored? Questions can be presented to us in a variety of ways. If we have the complete reaction provided to us, our first step is to analyze what we have to identify which chemical is the acid and which chemical is the base. If we don't have the reactants given, we have a little bit more work to do. This is quite an intense example. We need to locate the chemicals on the table. If we have a situation where the substances are amphiprotic, this chemical that's higher up in the acid column is the one that's going to behave like the acid. The chemical that's lower down in the base column is going to be the base. Then we can execute the proton transfer from the acid to the base to complete the reactants. And finally, in both of these examples, the acid was higher than the base on the table, so we classified both the equilibriums as favoring the products. And I hope that helps.